Hello, I'm Vincent Perlin. I'm a student here at TCNJ, and me and Dr. Lobson have been working on using generative artificial intelligence to predict machine behavior. Specifically, we're going to be talking a lot about wind turbines today, using AIs to kind of go between different data sets of wind turbine data. To how that means. This thing is not. Okay. So let's do a quick outline of how this is going to go. So we're going to start with like a motivation, like why we necessarily want to do this, why this is an important thing in the field and the uses. And then we're going to go over the specific type of network that we use and the way we use that network specifically. And then the future applications and the future things we can go with this once we finish what we're doing. So the motivation for this, like I said, we're focusing mostly on wind turbines. So wind turbines have a couple very unique problems that lend themselves really well to translations between different data sets. The one thing that's illustrated on this slide is about how there are different types of wind turbines, and some of them are much newer than others. So like there are smaller wind turbines that have been running for years and years, and there's a lot of data on them. We know exactly how they work, we know how they fail, we know all that kind of stuff. And then there's new wind turbines that are bigger and slightly different. And one of the questions we can ask is, can we train AI to take those? Can we train AI to take those older, smaller wind turbine data and use that to help predict and forecast how new models will run, how they will work, and failure points? Other things that are kind of in the same area and issues that we're exploring through the same kind of general approach is the idea of virtual sensing, which is basically that wind turbines are, for the most part, in like the middle of nowhere, right? You think of wind turbines, they're in a field somewhere out at sea or in mountains, like places where it's windy, generally not places where there are a lot of people. So it's very expensive to send out people to inspect them. Often it's very expensive to repair sensors when they break. So if you have a bunch of wind turbines that you don't exactly get all their sensor data, you only get the power output, can you use sensor data from other wind turbines near it to then translate that data into the wind turbine data to see if that wind turbine is operating correctly? Can you use AI to do that translation? And will, to really see if your wind turbines are acting correctly. And those two kinds of things are what these are illustrations. So the models we use are all variations of something called the Generative Adversarial Network, or GANs. So they're originally proposed by Ian Goodfellow. A lot of things you'll come to see in AI started with images or text. So this started as ways of generating images. Basically, you take in your model. You have two models. You have a generator and you have a discriminator, and these two models are adversarial, right? They're against each other. They're trying to compete to quote unquote win. So the generator takes in random noise and produces some image. Right, at the beginning, that's going to be nothing, but hopefully, after training, it'll start producing pictures of types of pictures that you want, right? And the discriminator, its only job is to figure out, is the picture I'm looking at real, or is the picture I'm looking at fake? So if you take, for example, if you have a bunch of pictures of some celebrity, right, of, let's say, Danny, right? You can take, you have a bunch of pictures of Danny DeVito, and you have a bunch of random noise that's going into your generator that's faking a bunch of fake pictures of Danny. At first, those fake pictures will be really bad, but your discriminator will also be really bad at telling apart the real pictures from the fake pictures. So then the discriminator looks at the pictures, says it's going to see a bunch of random noise, and it's going to think, I think this is a picture. And when it thinks, and you're going to be like, no, it's not. So that's some loss that it realizes, okay, so it's not that. So I need to change a little bit to make sure that I say that that's not. And then it looks at a real picture and thinks, okay, I think this isn't a picture, a real picture. But then you're like, it is a real picture. So then it updates that. And slowly over time, we'll get really good at telling apart real and fake pictures. And then this is useful for us for the generator because then its output is inversely proportional to the discriminator. So when its output is like when it has a really bad output, the discriminator is going to easily say, no, that's not real, and the generator says, okay, I need to do better. Or if it takes a really good picture, the discriminator is going to be like, actually, I think this picture is real, and the generator knows that it then fooled the discriminator, so it's doing something good, so it's going to continue doing what it's doing and continue producing pictures along those lines, right? Originally, like I said, these are used for images, and that's a classic example, just random noise going in, generating pictures, and then by the end, you just have a way of just generating a bunch of fake pictures from whatever data set of pictures that you have. But if we, yeah.
Next.
Okay. But the original use that we had was about motor signals, right? So basically, you can pretty easily, if you have a motor and you have all the different possible, that you have a lot of data from this motor and you have all the different possible fault patterns and all the different possible failure modes from one motor, you can pretty easily make a model that just takes in that motor's data and just tells you, what, like it tells you, how it's broken, why it's broken, and a bunch of really useful information. But if you took that model and took it out to a different motor that you didn't train it on, it would be completely useless, right? And because the model's trained on only specific motor that you are, was only trained on specific motor that you trained it on, the one that you have all the data set, and it's not really useful on other motors. So something we wanted to explore at first was, can you take another motor's data, and then translate it into our target motor to make it so that our model that can figure out the faults and the failures of the original motor, of the target motor, can figure out the faults and motors of the translate data from the source motor, right? So if you can see here, we have these two motors, and like I said, the target domain, we already have a model. You can already have a model that says, hey, this model, this motor, if I plug into I can plug into the model and says, this motor has a bearing fault, at this frequency, so you need to figure out, replace the bearing, right? Or it has some other kind of fault, some other kind of failure. And then we have a source domain, which has an unknown fault, but we have a model that can then translate the source domain to the target domain, so that we can then run the model on that translated data to then figure out the fault with the source domain, right? So it's kind of this translation action with GANs that we're trying to explore here, rather than necessarily just generate. So yeah, like this is what we're talking about, kind of just like the translation kind of action, making sure that so that we can have theory, any motor can translate to our target motor, so that we can classify, figure out faults, figure out why, like how it's broken, why it's broken, so that someone can easily just go and repair it, right? All right, so this is kind of how we can see the setup of the GAN to do this translation action, right? To go from our source domain to our or from a target domain to a source domain. So right, you feed in your data to the generator, right? And it will pop out some output, and then the discriminator looks at those two, the target and the source, the target and the generated, and it figures out, is it real, is it synthetic? And eventually over time, the generator will be really good at taking in your input and making it look a lot like your output, right? And it basically makes it so over time that you're doing this translation. You're taking your input data, you're taking it to your output data, so that it's you're taking input data, move to output data, so that it is doing that translation. So all the data is moved over, but it moves over and translates in such a way that another model can look at it and figure out what's wrong with it, right? And then we also have this tuna optimized model. That's basically just a model that goes through and changes how these generative discriminators are set up, because they're obviously set up in very complicated ways. They have many different layers, they have many different parameters, and figuring out what the optimized ones of those are, it's difficult. So you use something like Opportunity to go back into it to change around the different parameters to make it so that it trains and converges well, which is a difficult process that we'll talk about later. And in this example, you can kind of see by looking at, I mean, there's the raw numbers here, and then there's also kind of the eye test for this for over here, right? And I mean, by the eye, you know, the numbers, you can kind of see the source and the target and the polish. You know, obviously it makes it closer to what you're trying to get at, right? It makes it seem, you know, much more like the data. You know, it's doing the translation. It's doing much. It makes it seem much more like the data. The data they're trying to get it to work on, so that it could actually do it. But of course, if you look at it, it looks a lot more like it, sure, but it's still like the stem, right? And so there, like when you're just doing it this way with the one GAN, just going through, you still get problems, right? It does the translation, but like not completely. Right? It doesn't do it in a way that's completely like shifted, which is why we then move on to our cycle GANs. So cycle GANs are basically our innovation that was proposed by Zhu, which basically takes two GANs and points them at each other, right? So in a normal GAN, we have an input that we can then generate an output. And all we know about that output is it looks like the other things in that output domain. But with a cycle GAN, you can go in both directions, right? You have one GAN that goes from, we'll say, domain X to domain Y, and then we have another GAN that goes from domain Y back to domain X, right? So the idea is, like, if I have a bunch of, and of course we start with pictures, so if I have a bunch of Monet paintings, right, but I wanted to add a bunch of photos, you can train one GAN that can turn Monet paintings into photos, and then you can train another GAN that can turn photos into Monet paintings, right? And the idea with this is if I take a picture, right, and I turn it to a Monet painting, and then I use the other GAN to turn it back into a picture, I should get the same picture, right? These two GANs should be inverses of each other. If I go from one to the other back, right, I should get the same picture, meaning that these translations are like a one-to-one mapping, right? Each input has only one output because each output only has one input going through, making it so that it's more of a direct translation between these two domains. Now, for pictures, these are kind of obvious, right? Like, obviously, between a zebra and a horse, right? I mean, you're just going to take the zebra stripes and turn them into brown, just horse fur. Or if you take a horse, you're just going to turn the zebra stripes. But with our translation for our motors, it's a little more subtle, but it makes it so that, any motor has certain like flaws and inconsistencies with it. But then it has other like more broad-based things. We want in our translation to translate all like the more broad categorical things into the target domain while keeping the more subtle quirks about the motor the same, because that's where the faults are and that's where all the problems are that we want to measure, right? So these one-to-one mappings essentially assure that you're changing the things about it that make them different, but keeping all the subtleties, right? So it keeps the houses the same, but it makes it a Monet painting, right? Or it keeps the gestures of the horse the same, but it makes it a zebra instead. And so that's our goal with kind of these translations, which is why we started exploring cycle GANs for our wind turbines. So so this is kind of the principle that we're working on here. Basically, the first one we wanted to do is basically, can we take a bunch of simulated data on a simulated wind turbine, and can we turn it into, can we translate that between a real wind turbine with real data, right? So basically the point is, if I I can simulate tons of data, right? I can just kind of go in and I can run the computer for the weekend and I can just get, just hours of data for a simulated wind turbine, right? But real data is, maybe harder to come by. Maybe the wind turbine's new, or you haven't put a wind turbine in that exact location before. Maybe it's just like a certain company holds like weird copyrights with it. Maybe the sensor's broken. You just don't have the data. The data was lost, right? But you have tons of simulated data, so it'd be really useful for us if we could take that simulated data and translate it into real data, so we could figure out, what that real data, what that wind turbine should be doing. Figure out what that wind turbine characteristics should be, so that we can compare like the power output and things that we will always have the data for to make sure that it really is on track, right? And that's how we set up the GANs like this, right? So we have, domain X would be our real data, domain Y will be our generated data, and then we have the generator G, which then takes our X domain data, turns it into fake Y domain data, which is then put through the discriminator to see if 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 it thinks it's real, if it thinks it's fake, if it's good generated data essentially or not. And then you do have generator F that does the exact opposite, right? It goes, so you have these two things that go in opposite directions, and then there's this one extra loss that basically says that Y minus G of F of Y should always be 0, right? It should be as close to 0 as possible. Because G of F of Y, G and F are supposed to be inverses here, right? They're going in opposite directions. They're going, X going from Y to X, and G's going from X to Y. So any data point from Y should be identical to its G of F of Y, right? And the same thing with X and F of G of X, right? They should be inverses of each other. So that extra error there is the kind of the main point of how these cycle GANs work. So that sounds all fun in principle, but it is quite the pain to work with, right? You're training 4 different models all at the same time, and they all have their own quirks and inconsistencies. They all have their own it's not immediately obvious how each model should necessarily be set up, like as in how many layers you have, how many, what's your learning rate, and all the other stuff that you have to set for AI. So for just setting up an AI, so you run into kind of a few problems here often. So one is with traditional GANs, which is part of what cycle GANs try to solve, is the fact that with traditional GANs, a lot of times the discriminator the generator just ends up figuring out, oh, there's a couple images that are definitely in the data set. So if I just make everything look like those images, then the discriminator will think it's real because that's in the data set, and I don't have to worry about anything else. And that's obviously a problem, because if all of your outputs look exactly the same, you're not really doing anything, right? You're just, all your outputs are basically just saying, everything's fine, even if it's not fine. So trying to solve that is where the cycle GAN comes in, to make it a one-to-one mapping so that all the outputs don't look the same, and they actually do hopefully tell you something. Then there's convergence failures, which we struggle with a lot, where your generator and one of your generators or discriminators is just a lot better than the other, right? And for example, if your discriminator just says, if your discriminator always says, no, your thing's wrong, because the generator's just good at its job, then the discriminator's just good at its job. The generator will never learn anything, right? Because if its feedback is it's not real, it doesn't learn anything, it just does a bunch of random stuff, and you're never gonna get a good output. When on the other hand, though, if your generator is too good, then the discriminator, basically, it says it's gonna end up just saying everything's real, because it doesn't really know the difference. It's the same thing. The generator doesn't learn anything new, and it eventually gets to some point where it just stops. It stops learning anything really useful, because it doesn't, there's no useful output there because the discriminator can't learn what the actual difference is. Now, to address that second point, there's this thing called the Wasserstein GAN, where basically instead of a discriminator telling you either is real or isn't real, it tells you something a little more useful than that. It acts like more like a critic. Like instead of saying it's like the difference between Rotten Tomatoes or IMDb. And on Rotten Tomatoes, you either say I like this movie or I don't like this movie. On IMDb, you say nah, I think this movie was a 7 out of 10, right? But this movie was an 8 out of 10. So that's kind of what the critic does in WGAN. Instead of saying I think it's real, I think it's fake, I think it says something more like I think I'm going to give this a 7 out of 10 for being real, or I'm going to give it a 3 out of 10 for being real. So it gives you more, it gives the output more ability to kind of add nuance. So the generator's goal isn't necessarily to get the discriminator just be like, to say that's real all the time. Its goal is just to get as high as possible a score on its output, right? The kind of high as possible score as its critic response. Yeah, so now we're going to talk about like a couple more future oriented things to also help make the training more smooth. Because obviously we're talking about wind turbine data here, right? Wind turbines are bounded by the laws of physics, which we do and some of the data here is, for example, the position of the blades, right? Or the sway of the tower. And these things are all governed by, Newton's equations, right? So if we integrate, if we have position and then we, integrate it twice, we can get the actual equation for how it should be behaving, right? And within some bounds and some errors. But the point is, if it violates this equation, we know the output is automatically wrong, right? So we could add this into the model and basically punish it if it's far off, right? If it looks at this and it says, it says like this, like the left side of this equation is like triple the right side of this equation. We're going to be like, well, no, it's wrong. That these have to be equal. These have to be the same. So try it, and that's like, so we're going to add a big penalty to that. Just try and focus mainly on making this equation right. But if it does this and it says they're within 1% of each other, then it's like, okay, maybe focus on the other part of it. Like it's a smaller loss, and that means physically it's doing good. It's just maybe there's other parts that we're trying to print. This is just another thing that we add to the generator loss, right? So we have the discriminator, the cycle loss, and then now we have the physics loss. And hopefully all these losses, accumulate into it actually, focusing in on the exact thing that we're trying to do, which is this translation between the domains. These are some preliminary results to show kind of how this is supposed to work. So here we have, so the first and third ones are input data, right? So we have y and we have x. And the point is you're trying to make g of x look like y, because g of x is supposed to be a signal from the y domain, right? And you can see here in these preliminary results, it looks pretty close. Which is, it's a good and bad thing. This is kind of a little bit of a sign of something called overtraining, where it kind of just memorizes the output. But it's also good because it means it's learning something, right? And then you plug in that g of x back into f of x to go all the way back to see, is the cycle, is going from x to y back to x, does that change anything? And we ideally want our answer to be no. So we see f of g of x is very similar to x. And so that's kind of the goal. But like I said, these are just preliminary results, and there's so much more to do to make sure that it works in all cases and all situations and whatnot.
What are the signals? Is that vibration, temperature?
These ones specifically, I think they are position.
Tower top acceleration.
Yeah, tower top acceleration.
Yes.
So Yeah, right now, because I mean, this is just like one example of, in theory, you'd want this to be true for all parameters that you have, right? And there's like 12 of them, right? So it's like blade angle, motor velocity, or like turbine velocity. Then you have tower top acceleration, and like a vibration data. Like there's a whole bunch, there's a whole laundry list of them, but this one specifically, yeah, tower top acceleration. All right, so where does this lead us, right? So right now, we're doing data, we're talking about the simulation data versus a real test target of a 1.5 megawatt wind turbine, right? This is, trying to go between these two data points with the cycle GAN going between the two of them, right? But one of the applications that I mentioned at the beginning is using the data that we have from these, more prevalent 1.5 megawatt turbines to then maybe get data on what the output should be for a larger wind turbine, right? So, for example, if we can already predict what it was for a 1.5 megawatt wind turbine, what happens if we have a 1.5 megawatt wind turbine with then a different wind input, right? Can we use all the wind inputs that we have for that I'm trained on? Can it then extrapolate to new data and go out there further, right? That's just the simple validation that our model works, right? But then can it then go to a different type of 1.5 megawatt turbine, still fundamentally a 1.5 megawatt turbine, but can it then do the translation between a turbine that it wasn't trained on its data, right? Can it go further than that? And then the hardest one, which would be ideal, is then can it also predict between simulation reality of a 5 megawatt wind turbine? So basically, this question is more of asking like, are the translations between the simulation and reality fundamental enough so that the translations between a 1.5 megawatt simulated and real turbine are similar or the same as the translations you do between a 5 megawatt simulation and real wind turbine, right? So, and if that was true, and if that proves to be true, that'll be very useful because it means that new wind turbines, you can already say, or even before they start, or as they start, what should its output be? What should all of its sensors be reading? What should it all be doing? And if it's not doing that, having, like raising an error saying like, hey, something's wrong here, or this thing is wrong here. And and then like the long target is a 22 megawatt wind turbine, really extrapolating it out to basically the entire breadth of all wind turbine powers. So this is what I was talking about for more like application specific things. Like you can use the same translation models, right, fundamentally, as health indicators, right? Because all of your, if you have a bunch of wind turbines and say only half of them have their sensors working, right? The sensors break and it's too expensive to really go replace them. So, sorry, if you have half of your, the half of this ones with sensors, you can use this translation method to figure out what the sensors should say on the other half, right? And one of those things is, power output. That's one of the parameters that you're measuring. And if there's discrepancies between what the translation says that the power output should be versus what it actually is, that's some indication of some failure in the wind turbine, and is something to be investigated by a person. That's a sign that, hey, someone actually needs to go out there, someone needs to actually look on this. And that's used for a wind turbine company because it means they don't have to just send someone out to do that regularly because you already know they have health indicators saying, oh, when you need to go inspect this wind turbine, right? So anyway, that the actual math on figuring out like what the health indicator would be is this kind of thing, right? Basically, if you put it through the model, if it comes back with something that like it's different than it should be, then something's wrong. It means it's not part of a healthy wind turbine, which is what all this data is trained on. So this research was done partly through the Department of Energy, through the VFP program. hopefully that continues throughout the summer. Yeah, and then also John Kang still some of who works at the Department of Energy in their wind turbine lab. I know we did this research with it. Any questions?